Good evening, participants. Am I audible to you?
Good evening, sir.
Yeah, okay. Let me presentation. So I think this is sixth session, isn't it? So welcome to the seventh session of certificate and internship course on artificial intelligence and machine learning approaches of drug and vaccine design in cancer. So today we'll be discussing about molecular dynamics simulation. Okay, before going to the molecular dynamics simulation chapter, can we discuss the last session contents? So kindly recap the last session topics. IGF2 receptor and biomarkers. Yes, good. So we have gone for docking, isn't it? Molecular docking. We used what for molecular docking, we have seen day before yesterday. And yesterday we have seen how to go for docking analysis and docking validation, isn't it? How to validate the docking results. So how to first analyze the docking results, then we can come across how to validate the docking results. Can you tell me what is the software we use to analyze the docking results? There are so many softwares, but what software I showed you to analyze the docking results? Yeah, you got the answers. So my question at present is, what is the software I've tried for analyzing the docking results, like retrieving the hydrogen bond interactions and the other kind of interactions, like pi alkyl interactions, types of hydrogen bond other than that we also seen classical kind of an interactions, non-classical interactions. We have determined the bond length, isn't it? So what is the software I've tried? I think many of them are in the festive mood. Huh? But okay, I see that I can complete it today as soon as possible. But I need a kind of interaction, which makes me interesting to teach you. RxF software, good. You're trying very good, Veera Rahul. How about the others? Do you remember? I was explaining about BioVia Discovery Studio Visualizer, isn't it? So this is the software I used for analyzing the docking results. Whatever I docked in Autodock, I just analyzed it using the BioVia Discovery Studio Visualizer. And how about validating the docking results? What are the softwares or databases I've used? What are the softwares I used for validating the docking results? Softwares or databases? So my next question is, what are the softwares or databases we have used to validate the docking results? Pyrex is not exactly. Pyrex is used for virtual screening of multiple ligands with a single receptor. For validating, are we using PubChem? No, not. Then what? I told you that we can validate the docking results using PDB sum. You remember? I told you we can use PDB sum, and also we can validate the docking results by docking with control ligands. If you're using your plant compounds and if there are already existing a control drugs for a particular receptors, we have to dock your drug with the receptor initially, find the binding sites, and now you can dock with your plant compounds or whatever samples you're going to try, and just cross check, you validate whether the binding sites, whatever you retrieved, is same as that of control drug or not. So even that is one such validating the docking result. The other, I told you to use PDB sum, isn't it? Also, I told one more method. Um, so there is also one more method like using what if, what check. There are some tools, what if, what check. Using the tools also, we can able to determine the binding sites. Any doubts you can raise, can unmute and question me, or else you can just type the question in the chat box. Okay. So meanwhile, I can take you to this new chapter. And you remember in virtual screening, I also explained you how to dock some multiple ligands. For that, I have taken example nodes docked with insulin growth factor 2 receptor, like our Veera Rahul has mentioned. Good. So this is what finally we have concluded, isn't it? We have practiced using Autodoc PY-RX. Good. Let me take in to the MD simulation chapter 6. Molecular dynamics. What do you mean by molecular dynamics? Actually, the defaultly we call this molecular dynamics as a computer simulation method for analyzing the physical movements of atoms and molecules. So till now, whatever we have seen is a docking, something related to docking, that is about checking the binding affinity of a ligand with a receptor. But here, we are going to check with respect to time, as he earlier mentioned. So in this simulation method, we are going to check the physical movements of the simulation. Can be like, even if you put a protein molecule in an environment, can be like if you have a protein and if you put in methanol, how about the stability of your protein in methanol? And if you're putting in a buffer, what is the stability? And if you're putting in some isopropanol, what is the stability of a protein with respect to solvent? Even that is a kind of a MD simulation. So whatever we are going to analyze, we are going to analyze the physical movements of atoms and molecules of a macromolecule in that case. The same, even we can able to analyze after docking. Like if you dock ligand with the receptor, and even the interaction patterns with respect to time can also be analyzed using molecular dynamics simulation. There is also one more way of simulation used in computational biology. Like if you see 3D structure of proteins determined by gold standard techniques. So before going to this chapter, this topic, I like to ask one more question, most important question. What are the gold standard techniques used to determine the 3D structure of a protein? Used to determine 3D structure of a protein. What are the gold standard techniques? So whatever gold standard techniques you are going to use, I think one participant, Nandini, if you want to question, you can question me or mute. Your mic is not muted. Nandini Loganathan, kindly mute, or you can ask the question and mute it. Okay, I just raised a question at present to all the participants. What are the gold standard techniques used to determine 3D structure of a protein? Yes. Till now, I didn't find any answers. Homology modeling, good. You have tried, Tanveer. But homology modeling is a computational prediction method. In computational prediction method, we have seen 3 methods. But my question is the gold standard technique. So that is not a computational method. You are using some wet lab techniques to determine 3D structure. Very good. X-ray. If I take you to the X-ray, there also whether we can use the same X-ray what we go for scanning to find the bones in our body. That Tanveen has answered. It is X-ray crystallography. So if X-ray crystallography is one of the methods, the next method is X-ray diffraction. Good. And also NMR spectroscopy. Good. So we can complete the entire NMR spectroscopy. That is the method. Good. So whatever you mentioned like NMR is nothing but a spectroscopic method, isn't it? Okay. Till now we have seen 3: X-ray crystallography, X-ray diffraction. X-ray diffraction generally is for small molecules, but crystallography for macromolecule proteins. NMR proteins, but not that much big size when compared to X-ray crystallography. If you have a big size proteins, okay, like spike glycoprotein, better go for X-ray. And when compared to X-ray crystallography, there is also one more method which is often used. So this method often used during determination of 3D structure of spike glycoprotein during the pandemic times. So getting a crystallizing a protein is a very difficult task. If only if you crystallize a protein, then only we can take ahead with that sample in X-ray crystallography. The sample to be prepared for X-ray crystallography is more tedious. So one method is used. What is that method? Very good. The answer is cryo-electron microscopy. So this is a method we can use even for infectious viral derived proteins. Okay, cryo-electron microscopy. So I've gone to Indian Institute of Science and I've seen excellent facilities. So I think they are the first in India to establish these kind of cryo-electron microscopy facilities. Of course, they also have NMR, nearly 6 types of NMR. They have also X-ray. They have multiple. It's a very large institute, isn't it? So we have so many facilities in Indian Institute of Science, Bengaluru. Okay, so these are the gold standard techniques. Whatever protein structures determined from these techniques, you find the quality of protein is good, very good, nearly 100%. And whatever computational methods can be homology modeling, um, ab initio prediction, threading, whatever you're going to predict the 3D structure, you have to compare with the gold standard technique derived proteins. Then only you can determine how much quality of a protein is derived from the computational methods. Okay, so why I'm bringing all these concepts? I was explaining you something about MD simulation. So if you are deriving if we are deriving the X-ray coordinates, for example, so I can take you how the X-ray coordinates look like. X-ray coordinates of a protein, isn't it? Of a protein. So I can take you to an images. X-ray protein looks like this: a black and white scattering images. You have a protein crystal, okay, and if you see if and if you get a protein crystal, then if you I can zoom in and show you. If only if you go for X-ray, so whatever black and white spots you have, this will be immediately transformed into 3D structure of a protein. This can be visualized in a visualizer, isn't it? So we generally see alpha helices and beta sheets. So how this structure is derived only from the X-ray coordinates or whatever NMR coordinates. So whatever transform to the .pdb file, this file extension is different, this file extension is different. If this file has to transform to .pdb format, then you have to use MD simulation. Here also you have to use MD simulation to simulate to form this kind of a PDB format. So there are multiple ways of MD. There are multiple applications of MD simulation. But basically what it deals about the analysis of the physical movements of atoms and molecules. Okay, there is much description you can find in plenty of textbooks about MD simulation. Even you can search, if you want to study from the basics, study from Wikipedia information. You know, the MD simulation, the movement of particles, all these things are determined from the physics. Actually, if you see the MD simulation, this is derived from computational biophysics. Okay, not chemistry and mathematics. So majorly you should have a biophysics knowledge. So what is the equation we used for checking the movement? Defaultly, we use Newtonian's equation of motion. There are different equations of motion, isn't it? Newton's first law, second law, third law. So actually, we generally use Newton's equations of motion based on the particle, what type of particle and how the movement is happening on. Okay, so this is whatever we studied in physics, this is implemented in these softwares, in MT simulation softwares to determine the movements. Okay, so we study the movements using various parameters. Here you can see in this slide, Monte Carlo versus molecular dynamics. If you see amino acids of a protein in a 3D environment, in a visualizer, so the amino acids might be this might be a first position amino acid, okay, or this can be a second position amino acid, and after this can be a third position, like this. Whatever amino acids you can find for a protein, this is actually in a wave form. Okay, you can find this amino acids of a protein or spread in this surface, and the protein can be folded based on these wave patterns. Okay. Actually, I mentioned you, even the movement of molecules, including atoms in a protein in a particular environment, can be, if you subjected to a solvent like methanol, what is going to happen with the stability, and what is the stability of the same protein in isopropanol or some other buffer, isotonic buffer. All these things can be determined, okay, through simulating in the software, isn't it? So if you put these amino acids of a protein, these are present in the random fashion, okay, so where you can find this is a kind of a protein folding happened. Okay, and this is what shown. This can be determined through Monte Carlo simulation methods. Okay, and if you see the main areas of MD simulations in drug design, we can find conformational sampling. Under conformational sampling method, you can find applications like finding the binding pocket detection. So you can also find the binding pocket detection in the docking, molecular docking. I told you Fredfield algorithm is that. But with respect to time, whether is that a steady state kind of a binding you can observe. So whatever, if you speak about a steady state, obviously we have to think about MD simulation. So identification of transient binding sites that can be targeted in drug design. And it can be used for analysis of binding paths, rearrangement process. And related to energetics, we can not only determine the energy of a ligand separately, and after docking ligand with the receptor, what is the energy of the ligand receptor? Okay, what is the energy of a receptor? All these things can be determined even during simulation. We can also find free energy calculations, perturbations. The free energy perturbations of each and every atom of a particular protein can be determined using the MD simulation. So how this can be determined? This can be determined using trajectories, energy trajectories. You know, if you have a protein of insulin of 113 amino acid, each and every amino acid you find plenty of atoms, isn't it? So each and every atom of a particular amino acid of even a small protein like insulin can be determined through atom trajectories. For 113 amino acid, if you have 1000 atoms, all the 1000 atoms are initially determined through energy trajectories, and then we go on for various mechanics methods. If you see the mechanics, okay, there are three types of mechanics. Number one is classical mechanics. Number two, statistical mechanics. Number three, quantum mechanics. You know, in mechanics, there are two types. One is statics and the other is dynamics. In mechanics, you have statics and dynamics, but majorly, if you study MD simulation, we focus on dynamics. Okay, the dynamics is the movement. Statics is at the same position. If you study the energy, we call it a statistic. We call that as a statics. Got it. Classical mechanics, we basically go for classical dynamics, and statistical mechanics is statistical dynamics, and quantum mechanics is studied in the form of a dynamics. So, what do you mean by quantum mechanics? If you see the classical mechanics, whatever I told, okay, earlier, that is a Newtonian law of motion. What is Newtonian first law of motion? You know that. Sorry, I can't able to write it. Uh, can I use some other thing? I can use the same, whether I can able to write now. Yes, F equals M A, isn't it? Force is given as the product of mass and acceleration. This is what, if you study about this equation, we call it as a classical mechanics. And if you study, if, I told you an example, like if in 1000 atoms, and if you calculate all the 1000 atom forces, okay, then we obviously we study in the form of statistics, because we have so many, plenty of atoms. So we can deploy statistics to calculate the forces. So that is mechanics. And after the classical, you go for statistical, and the last one is the quantum. What do you mean by quantum? Of course, this is latest, which uses almost also classical and statistics. So first of all, what is quantum? Quantum is derived from light, isn't it? Quantum mechanics differ from classical mechanics in that the energy, momentum, angular momentum, and other quantities of a bound system are restricted to discrete values. So generally, what kind of wave motions we can observe with respect? Here we observe wave particle. Here we instead of simply assuming an atom is a spherical one, and in an atom you have electrons, neutrons, protons. We have so many models, isn't it? Bohr model, Bohr atom model. We have the types of atom models. This is how we generally think, isn't it? But here in quantum mechanics, we assume the atoms follow the wave motions. So here we also have uncertainty principle. The motion of an atom can't be predicted unless how it is fitted to the support and what kind of momentum and what kind of force we have applied. Okay, so it depends. So related to quantum mechanics, so more about this you can see here. One ball is fit with the support. Okay, I'm going to stretch here. If you see A and B, the same kind of thing is there, but the same kind of particle is moving exactly for to and fro. But here the motion is slow. Here the motion is more and it is stretching more. So obviously for this motion, you find this kind of wave motion. Okay. But for this, you find this kind of wave motion because stretching and expanding, if you find one is stretching, the orange is stretching, the blue one is the expanding one. Okay. So what is going to happen if you take a harmonic oscillator, a pendulum in the clock, how it rotates in the wave motion. Similarly, here also I found a particle is following a wave motion. Okay. So you can find the variations with respect to motion in terms of waves. So if you see the waves, how the energy can be calculated here, the energy can be calculated using sine, cos, tan, and even inverse of all these three. Okay, generally this is what we use for the wave motion. So this is how the Scoroidinger has described a wave equation, and initially the drug design software came to market was Scoroidinger. Then why they kept the drug design software as Scoroidinger? Because it follows the quantum mechanics principles to determine the MD simulation. So obviously they named it as it. Okay, so the Schrodinger wave equation is a particle duality equation, wave particle duality equation. If you want to understand in layman terms, if you want to determine to layman terms about quantum mechanics, I provide you with an example. Like if I give you a sample of protein, okay, in a cuvette or in a Eppendorf, so how you determine the molecular weight or how you determine the weight of a protein? The weight of a protein generally determined through measuring absorbance in spectrometer, isn't it? How we measure? You fill the protein sample in the cuvette and insert into the spectrophotometer, and then you try to pass the light. If you pass the light, obviously you observe the absorbance. Even the same principle apply for the colorimeter, nephrometer, fluorospectrometer. Light has to be used to determine the properties of a protein, isn't it? So this is an example. Okay. Whatever we use in MATLAB, if you want to correspond it to the computational thing, the same kind of a computational things, but we use a kind of the classical statistical and quantum mechanics. Okay. And if you see, there is one technical term called force field. I was explaining you that if you have an insulin of 113 amino acid and if you have totally 1,000 atoms, for each and every atom, the force has to be calculated. If you calculate the force of all the atoms, then we sum up to form a total force. Whatever total force you calculate, from the total force, if you want to calculate energy, How you can calculate energy? You know, the force into distance. Sorry, I can't able to write it properly. Energy is given as force into distance, isn't it? This is the formula. So the same formula. So what is force field here? It is a computational method that is used to determine the forces between atoms, within molecules, and also between molecules. Not only within molecules, but also between molecules. And if you see this force field, there are plenty of force fields. Classes, there are classifications of force field. We can see one by one. Okay. So can we go to the number one? So before going to the number one, you can see also the types of force fields. I told you force fields are nothing but forces of each and every atom. So the forces, we calculate bonding forces, non-bonding forces. We sum up both the bonding and non-bonding to get the total bonding force. Okay. Now we see the types of force fields: classical, polarizable, reactive, coarse-grained, machine learning, water, modified amino acids, and other types of force fields. Classical force field. This is the first one we see in more information on that. So there is one method called AMBER. AMBER is a force field, and also in this name we also have MD simulation tool. It's a package, of course. AMBER is assisted model building and energy refinement. This is generally used for finding the used for MD simulations of protein and DNA. There is one more popular field called consistent force field, CFF. A family of force fields adapted to a broad variety of organic compounds. Okay. And also this is used for polymers and metals. If someone is studying about material chemistry, then they can go for this kind of CFF. Charm, widely used. In Gromax default, we use the charm. And if you see Discovery Studio, the commercial software BioVia product, you find Amber, CFF, charm, MMFF. All these things are defaultly built in Discovery Studio. We can choose the MD simulation method that is a force field, and we can use it accordingly. What is charm? Chemistry at Harvard Molecular Mechanics. This was originally developed at Harvard, widely used for both small molecules and macromolecules. So an amber for macromolecule, isn't it? CFF for a small molecule, isn't it? But charm we can use for in both applications. Similarly, we have CVFF, Gromos. Gromos is Groningen molecular simulation. Okay, so Gromax use charm, and also we can use a Gromos. This is an option for it. IFF, interface force field, Merck molecular force field is MMFF. OPLS, optimized potential for liquid simulations. So different universities have developed different force fields under classical force field. Now polarizable force field. This is a second major category. In polarizable, we also find amber, amoeba. There is an expansion for amoeba, atomic multipole optimized energetics for biomolecular applications. Charm, polarized force field, SS-based chemical potential equalization, phased, orient. If you want to study about the force field and the energy minimization and the types and methods, okay, all these things you can study from Molecular Modeling by Anand Solomon. This is a textbook I can prefer you to study about more about the theory concepts. Now go for the third major category of force field, reactive force field. If the ligand, when bind with the receptor, if it's going to react, for example, if a substrate is binding with an enzyme, what is going to happen? Enzyme substrate is formed, isn't it? I can take you to the Word, Microsoft Word, and I can explain you. So I zoom in. Now I can explain you. Generally, enzyme, okay, enzyme of particular concentration reacts with substrate, okay, to form. It can be a reversible reaction also, of course. energy substrate complex. An energy substrate complex, okay, can able to generate enzyme, which is a reversible nature, and also instead of substrate, you will be getting product, isn't it? So this is how we generally find in enzyme substrate binding. Okay, this can be a reversible one, but this is irreversible. If product is formed, only the energy alone you can use it. Okay, whatever product you derive, you have to take extract out. Okay, so what is happening there in that example? Reaction is happening on binding of substrate with enzyme. So for this, better go for EVP. If you work on enzymes, go with EVP and reacts FF. This one more example. And coarse grained force field. The name itself say coarse grain. Wherever you find some kind of a grains in the sample, for example, DPD, dissipative particle dynamics, is used to study hydrodynamics of various simple and complex fluids. What do you mean by fluids here? Can someone tell me what are the phases? We have studied types of phases, isn't it? What are the phases we can observe in fluid? My question is, what are the types of phases observed in fluids? Can you type the answer? It looks silly, isn't it? But still, you have more reasoning. What kind of phases are fluids? You can unmute the answer or you type the answer. What are fluids, of course? My question is, what are fluids? Still, I'm not getting answer. Good. Ajay Krishna is trying liquids, non-ideal liquid. Okay, liquids, ideal fluid, non-ideal fluid. Okay, I'm not asking about the classification ideal or non-ideal. I'm asking you fluids. Ajay has replied liquids. I accept. But is that only liquids or fluids? Is that only liquids or fluids? The others can also try. Yes or no? Solid, plasma, good. Nandini came up with all the answers. Your answer is right. But you are telling solid is also a fluid, isn't it? What kind of solid is a fluid? Other than liquids, of course, you should not miss the gases. Liquids and gases, obviously, we know that these are fluids. But solid is also a fluid. What is a fluid of? What is the property of a fluid? If you have a beaker, if you can able to, yeah, there is no proper shape, but it occupies a shape, obviously. For example, if you have a beaker, if you fill a liquid like water, so the water assumes the beaker shape. Ability to flow, of course, is also a property of a fluid. Not only ability to flow, but also it should get a shape, isn't it? If you have a container, if you fill a water, it gets the container shape. If you fill a gas, then obviously even the gas will be occupied accordingly, even that is going to have the container shape. How about solids? Not all the solids, but the solids like talcum powder, very fine solids. If you see the flow property of the fine solids, the flow property is similar to that of liquids. The very fine talcum powder, not all the solids. You can't see in the sand, mud, etc. Only in the fine powder like talcum. Okay. So now we can go to the presentation. So I was explaining you about coarse grained force field. You got it? So if you're working on complex fluids, okay, not only limited to liquids, but the other types of fluids, whatever I mentioned, better go for this kind of coarse grained force fields. Okay. Martini, Syrah, VAMM, these are sub-methods of that. So till now, whatever we discussed or about the force field, now we go to the energy minimization. So generally, I told you we have to calculate energy from the force. The force into distance. The distance is distance between center of radii of one atom to the center of radii of the neighboring atom. Okay, so this is how we calculate the energy from it. And the purpose of doing energy minimization is to bring the protein or molecule in stable form. If you have negative maximum energy, okay, then obviously can tell the protein or whatever your molecule you brought in stable form. You have to get more negative maximum energy. That's what we call it as energy optimization. Also, this called as geometry minimization or geometry optimization. So basically, we classify it as a steepest descent conjugate gradient. More about this, let us go for studying any textbooks or study for the basics from the Wikipedia. And machine learning. So I think this I can explain you in detail in the subsequent sessions. Molecular dynamic simulation, I told you, atom trajectory at microscopic level is what a classical mechanics. And generally, you use a classical mechanics if you have plenty of data to calculate statistics through statistical mechanics. And finally, we determine the properties at macroscopic level through the quantum mechanics. Okay, for a single protein, you get a absorbance in spectrometry, isn't it? So what is going to happen? You're determining the properties at macroscopic level. You're not going to determine for a single atom or a molecule, but you're determining for the entire protein. And if you see this kind of AMD simulation softwares, these are the software generally used in worldwide. Abalone, Amber, Chom, Desmond, Gromax, Gromos, and AMDQ, Yasara. AMD simulation in Gromax. You know, Gromax is a freeware, but we have complications in installation and running this freeware. Gromax's use, Gromax software use GPU. So for GPU kind of systems, you can use only desktops. Don't rely on laptops. Even if you have i9 laptop with a 32 GB kind of a RAM and some kind of a cores and threads with high configuration, still you may or risking your laptop. So better go for workstations or server to install this Chromax. So running the job in Chromax may take 1 day to 7 days. Also, it takes 14 days based on your capacity of your workstation or server and based on the input parameters you feed. Okay, of course, not only it needs the GPU, you should have a graphics card with more capacity. And if you see this kind of AMD simulation in GROMAX, it is a versatile package to perform molecular dynamics. Okay, millions of particles dynamic motion can be calculated. And generally in GROMAX, you find various outputs. These outputs or can be visualized. Only the outputs can be visualized at last through a software called XMGR. So only through this XMGR, we can able to plot the graphs of AMD simulation. So not only the GROMAX is just a software, but if you want to work GROMAX and if you want to find the final outputs, you have to link with more than 9 to 10 softwares. We need, in addition to the GROMAX and XMG, Grace, we also need few more, nearly 8 to 10 softwares. Of course, running the GROMAX needs knowledge on Python programming and Perl programming. Okay, so this is something about MD simulation using GROMAX. Molecular simulation was performed using GROMAX from docked molecules. Actually, I'm taking a case study. I have done plenty of studies with the MD simulation using the GROMAX. Okay, for running the MD simulation, nowadays for publication, they are expecting minimum to run for 100 nanoseconds. Okay, many of them are trying for 200 nanoseconds and 500 nanoseconds for high impact factor journals. If you increase the time to 200 or 500, it take double the time or 5 times the time, whatever you run for 100 nanoseconds. Got it? So if you're getting an output for 2 days in 100 nanoseconds, for getting output for 500 nanoseconds, it may take even 14 days. or 7 days. Okay, based on the protein molecule size. And the MD trajectories were saved every 1 nanosecond for analysis. So if you see the kind of scale, even if you're running for 200 nanosecond, so every trajectory is going to save for 1 nanosecond. So 1 to 200 you can find the form of a scale. So this is how I run for a research paper, that is I dock Nipah virus epitope with a human HLA molecule. So for this, I've used these as a parameters. So what are the things I calculated? RMSD, root mean square deviation, root mean square fluctuation, and other parameters. Okay. So if you see the GROMACS tutorials, okay, so before going to the output, we can also see a kind of information on GROMACS. What are the types of simulation we can able to run? So tutorial one is, there are actually six free tutorials, free sample tutorials to first work with GROMACS. If you install GROMACS in your workstation, number one is lysosome in water. And if you want to check the effect of protein molecule on lipid membrane, we can able to check it. Okay, lipid bimembrane and umbrella sampling, biphasic systems. If you have two different phases, want to check your effect of your molecule, and if you after docking, if you want to check how what is the stability of a ligand with respect to protein in the binding sites with respect to time. So this can be determined through MD simulation and free energy observations. So these are some of the examples. If you click inside the GROMACS homepage, if you find this kind of a picture, if you click the picture, obviously take you to that tutorial. Okay, so this is some information on the GROMACS tutorials. So now I take you to the ligand receptor MD simulation. There are totally 9 steps actually if you go for MD simulation of ligand receptor complex. So initially, you should have a ligand receptor complex as the input file. Like whatever output is generated from the MD molecular docking using Autodock or any other tools, you have to take it as a input in step 1 onwards. You have to start from step 1. So you have to prepare the protein topology, you go for prepare the ligand topology, step 2, go for defining the unit cell and adding the solvent. Default we add solvent to water if it is a liquid. If a protein is something in a, it's not a protein, if you're studying about a gaseous phase, then obviously you have to take air as the medium. If you take a liquid protein, obviously you take water as the control medium. And the step 4 is to add ions. And fifth step is to go for energy minimization. Sixth for equilibration, part 1. And there is also one more kind of equilibration you do in step 7. In production MD, it takes much time. So all these things can be completed within few minutes. But if you want to run the production, it takes, this only takes 1 day, 2 day, or 7 days to 14 days. And finally, analysis is easier. If you have exam grace, you simply, after running the production MD, molecular dynamics, you simply have to open in the software and execute it. If you see the MD simulation protocol, okay, generally the simulation, the GROMACS is installed only in the Unix or Linux operating systems. The GROMACS is not meant for Windows. So one should have a knowledge on Linux to work on MD simulation using GROMACS. If you see this kind of a, there are different programs. There are different, each and every program is maintained. The participant can kindly mute. Yeah, so there are, yeah, who is that? Jovisha. Jovisha, can you mute? Yes, I think she is muted. Now I take you to the presentation. So there are different programs in the GROMACS itself to run on different parameters. If you want to run, if you want to generate a topology for the ligand and receptor separately, use GMX setup program. So you have to, this is a command actually. You can use the command and you can execute this kind of a file. Execute this kind of a program. Okay, and GMX solvate is a command used to execute this kind of a program. This is used for solvating a system, and GMXEM for energy minimization, for GMXSIM for MD simulation. So restraints, the calculating position restraints, index for calculating an index file, extract energy components, process MD trajectories, structure configuration, all chemical free energy simulations, process input files. So finally producing GROMAX topologies with ACP. We have these kind of programs. Of course, we use the commands in the Linux terminal to execute these programs. So what is RMSD? I was telling this one of the output derived from the MD simulation. Root means quantization, I told you, but what is it? It is is the measure of the average distance between the atoms, usually the backbone atoms of superimposed proteins. If you have a protein, okay, if you want to check the quality of a protein, the quality of a protein can also be determined through RMSD. Not only this quality of a protein, the structure of a protein quality is determined through RMSD, but also if you are docking a ligand with a receptor, and if you want to check uh, the stability of ligand receptor complex, that is for that also you can use RMSD to calculate the stability. Okay, RMSD has plenty of applications. One is to check the quality like the quality measures the stability of a protein, and number two is to also check the stability of a ligand receptor binding. So to work on RMSD, of course, you have to use a GROMAX command. How to use this? GMX spacebar RMS, and this is a parameter -f, and use the kind of XTC protein file and a PDB file and RMSD.xvg. Your output is going to save as RMSD.xvg for the ligand receptor complex, and simply open it. Okay, and to calculate the RMSD, this is the formula we use. And the RMSD graph in XM grays looks like this. So here I run for 200 nanoseconds, and this is one such a kind of an output. If you see the RMSD in the next slide, you have seen in two different colors. This is an output derived from a published paper. So I told you on yesterday that I worked Berivnon B docked with the two different receptors of hepatocellular carcinoma. One is epidermal growth factor receptor. You know, if your compound is docked with EGFR, it is shown in red color here. And if it is not docked, I mean, you have only EGFR in black color. The black color shows the EGFR protein alone, but this is an BB-EGFR complex, the red color. So if you want to infer the results of RMSD, the how much, if you have a minimum RMSD, you can tell that is stable. So after docking BB with the EGFR, you find the RMSD is less when compared to without ligand, isn't it? So our compound is having a better stability with EGFR. You understand? In black is just the protein receptor, but the red is ligand with the receptor, but the RMSD value is comparatively less with the receptor alone. So we can conclude that our ligand is docking well, is having a better stability with EGFR. And there is also one more output, like the stability can also be measured through the time. Okay, so if you see here, so from here onwards, you can find it's somewhat stable. Okay, it's not changing, isn't it? So what is the exact time here? If it is 20,000 picoseconds, this is 20 nanosecond. So it's almost and during 15 or 19 nanoseconds. During the 19 nanoseconds, you find a stable complex. But you can find a variation here. So only from here, you find a stable. So you find one in 90 nanoseconds, and the other time is around 42 nanoseconds. So the second interpretation is based on where you are getting a perpendicular line without much variation. Okay. And similarly, this is for caspase 3 receptor. I think 90 nanoseconds is for this caspase. And for this is around 50 nanoseconds. Okay, I have to check. You can check from the publication already published. And MD simulation RMSF, root mean square fluctuation. Actually, this is a measure of the deviation of the position of a particle line with respect to reference position over time. So RMSF is generally calculates the C alpha fluctuations, carbon alpha fluctuations. If you see this RMSF versus number of residues, okay, you find more fluctuation in this, okay, nearly at 100 to 110 amino acid, okay, find more carbon alpha fluctuations. So your protein is not stable only in these residues, okay, 100 to 110. But here you have minimal peaks. This is no problem, but here you have a major problem in these residue positions, 100 to 110. Got it? So how can we execute this? Using GMX command, of course, you use RMSF, then only you will be getting RMSF output. Finally, you save it as RMSF.xvg. And root mean square fluctuation from a case study, like whatever I ran for RMSD, the similarly I run for RMSF. So here you can find similar in these residues, you find more fluctuation with ligand. So whatever shown in red color is binding with ligand, isn't it? So in this amino acid residues, nearly 860 to something, 850 to 860 residues, you find some C alpha fluctuation. Similarly, here also nearly 170 to 190 per caspase 3. Okay, here you have fluctuation, but the remaining role somewhat negligible. And there is a third output called radius of gyration. What is radius of gyration? Okay, it just determines about the momentum. The radius of gyration is about the axis of rotation, which is defined as the radial distance to a point which would have a moment of inertia, the same as the body's actual distribution of mass, if the total mass of the body were concentrated there. So the moment of inertia is generally determined. Okay, so how, whether if you fit a fan, okay, in the ceiling, whether if the fitting is not good, then you can find a wavering motion and a noisy kind of a motion with the fan, isn't it? Whether is it rotating exactly in the center or not, or if it is having a kind of a wavering kind of a motion, if it is not fitted, then you can find some kind of moment of inertia is disturbed, isn't it? So that is something about radius of gyration. Okay, like however I told you an example, this can be determined through GMX rate. And binding free energy. The binding free energy can be calculated through, I think first I can skip out this card. Just have 5 minutes to complete. Yeah. This can be calculated through different trajectories information. If you want to calculate linear interaction energy, so the linear interaction energy can be calculated as the sum of two different. Actually, here the yellow color is the receptor and red color is the ligand. So for this, you should have a knowledge on ligand receptor in energy, and you should also have a ligand energy alone. Okay, for this, if you want to calculate, this is what I'm telling as a two trajectories. If you have these two terms, then obviously you can able to calculate the give free energy, the binding give free energy from this. And if you see one trajectory, okay, you should have only a ligand and receptor energy. This alone will calculate as give free binding energy. But there is also we use three trajectories. That is, if only if you have energy of ligand receptor bond complex, and if only if you have energy of a receptor and energy of a ligand Then only you can calculate the binding energy. So how this can be calculated? For three trajectories, you can calculate through del G binding is del G of complex minus del G of receptor minus del G of ligand. For three trajectories, you use this formula to calculate del G of binding. And this can be calculated either through MMPBSA, that is molecular mechanics Poisson Boltzmann surface area, or molecular mechanics generalized bond surface area. So this is also one kind of an output we can generate from MD simulation. You get in the form of energy in kilocalorie per mole in GROMACS. So MD simulation in GROMACS, this is a kind of a predicting the super secondary structure. Even super secondary structure can be predicted, and even the area with respect to time can also be predicted from the GROMACS. Okay, this is something about MD simulation using GROMACS. If we want to run this, I told you already, it's not feasible with my laptop. You know, in IIT Madras, I'm working on a DST funded project. I got a kind of a workstation to work with my project funding. So I am working on GROMACS facility in IIT Madras. If anyone are interested to work on any of the computational tools, including the GROMACS or any other thing, you are welcome to approach me. Of course, we are doing all these things through consultancies, through payment basis. Okay. Anything else to be? You want anything else from me? If you have any doubts, you can ask me. Or else, in last slide, it's written constant temperature and constant pressure in computer. What is that? Constant pressure and constant temperature. Which slide is that? Constant pressure, temperature. I'm not getting. Oh, which slide are you? Can you tell me the constant? Yeah. You are telling like in MD simulation, we use these parameters. We assume these parameters like constant pressure and constant temperature. No, we are putting a molecule in a kind of an environment, can be a buffer. We are going to check the properties, isn't it? Especially energy. Then obviously we should keep some parameters as constant, basic. We put in basis, isn't it? So the basis is a constant pressure and constant temperature. Like even if you want to calculate the molecular weight of air in chemistry, what you do? You have some standard properties. So you keep volume as 22.4 liters and you keep temperatures 273 Kelvin. Similarly, here also we keep a few parameters as constant. We use, I think, 25 degrees centigrade and pressure also 1 atmosphere. These are the constant parameter, constant conditions we use, the pressure and temperature. Okay. The softwares, we have to use computational biophysics to develop it. And of course, we are using that after that. Any other doubts you have, participants? So very good. Today also I have interacted well. So happy Makara Sankranti and Pongal holidays to you.